So, one of the unique advantages of having an auditory sense is the ability to get information from far away or out of sight. Like, with vision, you can't see around corners or behind your head. But Audition can give us info from any direction in all three dimensions, even if there are objects in the way. In fact, we can even hear the distance of some objects when sound bounces off of them, and with a lot of practice, humans are capable of some rudimentary echolocation. But in order to do stuff like this, or even just to hear a car approaching from behind or a skateboarder about to come around the corner, we need to be able to localize where a given sound is coming from. So I want you to think about, how do we manage to do that? Even with your eyes closed, you can often tell clearly that someone is saying your name right behind you, or that a car is approaching from your left, or a bird is chirping from the tree above you. So how do you think we manage to localize sounds? And when, in what kind of situations would we be bad at it? In other words, what kind of variables might affect how well we identify where a sound is coming from? I suggest you pause the video for a minute before going forward and speculate on some possible answers for those questions before we move on. So, in general, there are two primary sources of information that tell our brain where a sound came from, and thus also how it's moving. First off, we're going to see how some of the info, the hints or the cues that the brain gets will come from comparing what comes into each of our ears. We'll call these binaural cues, bi for two, because it comes from having two ears. We'll also see that the brain uses monoral cues, or one ear cues. These are sources of info that could work even if you're totally deaf in one ear, or one ear cut off and damaged, though of course it's the combination of these binaural and monoral cues that give us the high level of performance we're used to. So losing any of these sources of info will lead to worse performance for sure. Note that also, of course, we'll use info from other senses that could help us localize sounds, like cues from vision or head movement and things like that, but we'll save those details for later. Let's start with the binaural or two-ear cues. There will be a couple of them that are really important. For one thing, I want you to imagine a sound off to your left. Like imagine a sound coming from off to your left. It's going to go straight into your left ear, no problem. But to get to your right ear, it's got to go through and around your head, right? That obstruction means that the amplitude of the sound is going to be smaller when it hits the far ear. So basically, the sound will be louder in the close ear, quieter in the far ear. So that is one hint to the brain, oh, the sound is coming from this side because it's louder on that side. Now, as a side note, this actually depends somewhat on the frequency. So with low enough frequencies, remember low frequencies like a low pitch, at low enough frequencies, we're talking about sound waves that are actually pretty far apart to the point where the head won't block them as much. So with really low frequencies, it requires bigger objects to do that blocking. The head might not be enough, so there will be a much smaller effect here, much less of what we call an acoustic shadow from the head. So the effect is going to be biggest for higher frequencies, and we can actually see that it shows up in experiments when we bring people into a laboratory and do this in like a controlled sound chamber. What we might do is play a sound, like the exact same sound at the exact same volume, but play a sound from the side while trying out different frequencies. So we could manipulate the frequencies across different sort of conditions of the experiment. So notice what happens in the condition with like a high frequency, like the red line here for 6,000 hertz. That might be one condition of the experiment. For a 6,000 hertz sound, we're going to play it from all these different angles, right? 0 degrees or 180 degrees would be right in front of the person's head or right behind the person's head. Of course, that means it's hitting both ears with the same volume. There's no difference there. But if we measure how much volume there is when it hits their ears from the right, let's say we're 90 degrees to the right or something like that when playing a 6,000 hertz sound, you can see that there's actually a pretty big difference between the volume when the sound reaches the right ear and when it reaches the left ear. Which again, we can do this with a simulated head and just put two microphones here, or we could actually put microphones inside the person's head if we want to measure it. But what we find is about 20 or more decibels of difference in terms of how loud the sound is when it comes from the right versus the left. Again, if we're talking about a high-pitched sound, something in the frequency of 6,000 hertz. But 20 decibels louder in your close ear, that is 10 times as loud. Remember, decibels are on a logarithmic scale, so a jump of 20 decibels is literally 10 times as much amplitude. So 10 times as loud when it hits the close ear versus the far. But look at the yellow line on the graph here, and you'll see that it's a much smaller effect when we're talking about low frequency sound. It's only a little bit louder in the close ear, maybe 3 to 5 decibels. Still enough the brain could figure it out, but it's not as obvious. Thankfully, there is another important source of information that we get as a binaural cue, in other words, from having two ears, and that's the fact that sound will not only be louder in the closer ear, but sound will also arrive earlier in the closer ear. So this is the second binaural cue that's really important. I want you to kind of think about like if a sound is coming from straight ahead of you. Like in this little diagram here, imagine a sound coming from point A. It's equidistant to both your ears, so it's going to hit them both at the same time. But if a sound instead is coming off from one side, if it's off to the right, like point B here, it's going to hit your right ear first, just because that's less distance. You can measure it with a ruler if you don't believe me, but B is going to be closer to the right ear, and because it's less distance, it will hit that right ear first and arrive slightly later to your left ear. So that delay can tell the brain which side a sound came from. Both these two cues together kind of help for that. However, there is kind of a limit here. Those two things, the time difference and the volume difference or level difference hitting the ears, those can really tell us, they can only really tell us which side a sound is on. They're not as good at things like up and down. So for things on our left side, for example, they can't tell us whether that sound is coming from left and above and left and below. In fact, the two binaural cues that we talked about, they're going to be the same for a given sound coming from anywhere on the circle you see here. In fact, anywhere from all the circles that make up this sort of cone coming out of the guy's ear here. We actually call it the cone of confusion because there's an ambiguity there with just those binaural signals, those two ear signals or two ear cues. We can't tell the difference between the same sound coming from up here or over here or down here, just like I couldn't tell from this point, this point, this point, or this point on a sort of closer, smaller circle to the head. They all are kind of similar. So we need more info. Specifically, we'll need some more info coming from the monaural cues, the one ear cues, which I'll get to in a second. But first, before I dive into those, I want to give you a feel for how the brain could take something like sound hitting one ear a little sooner than the other, and from that, deduce which side it's coming from. Like, how is that done at the neural level in the brain? And we're gonna do this by walking through a simple neural network of just 9 neurons. And this is kind of theoretical, right? This is just a model, but it'll show how this can work. So these 9 neurons, I want to show you how just a handful of neurons, it doesn't have to be 9, but a handful of neurons could be enough to encode something like how far to one side a sound source is. I want you to imagine these 9 neurons that we've set up are in a little module in the brain somewhere, and they're getting signals from each ear, right? Because wires come out of the ears. The auditory nerve has a bunch of neurons going from the ears, from the cochlea, into the rest of the brain. So imagine somewhere in the brain we're at a place where we're getting wires from both of the ears. So we're getting a signal from both ears. Now imagine that each of these neurons is set up so that it only fires, or at least so it fires strongest, if it gets enough input all at once. Specifically, you can see it kind of has a connection from both the left ear and the right ear wires. So specifically, maybe it has to get a signal from both of its connections, the left ear wire and the right ear wire, at the same time in order to go off. So just getting info from the left ear isn't enough to turn on any of these neurons. They'll only turn on if they're simultaneously getting input, getting a signal, getting an excitatory connection from both the left and the right ears. So if a sound is coming from straight ahead, like we can kind of see in this diagram here, let's say we just play a sound from straight ahead where it hits both ears at the same time, then the signal is going to come in from the left and the right ear at the same time, at the same rate. So they're going to meet in the middle. Basically, the first place at which one of these neurons is going to be hit simultaneously with those two signals would be neuron 5 right in the middle. So this neuron firing, neuron number 5 firing, is a reliable indicator of sound that's not to either side. In other words, sound that's, straight ahead or maybe straight behind you. But if a sound hits, say, the right ear first, then that right wire is going to get a head start. It's going to get further along the pathway before the left ear gets the sound and starts its firing. So now what would happen if the sound was off to the right is the head start in this kind of red one means they're actually going to meet further off to the left in our little neural network, maybe neuron 3, right? So if the sound had been even further to the right, imagine we were playing directly to the right, not just a little tilted to the right, but 90 degrees off to the right here, then maybe it would even start sooner in the right ear, more of a head start, and they would meet even earlier, like at neuron 1 or 2, right? So these 9 neurons here, or something like it, would be a pretty reliable way to indicate how far to one side or the other a sound came from. Now, that's like a simple model of how this might work. Obviously, like it might involve more neurons in reality, like a bigger set of neurons to do a network like this. And it could happen in various parts of the brain. I kind of want to just review for a second and get you thinking, like, based on what we already know about the pathway that auditory information takes, right? Going from the cochlea to all the other places it goes, where's the earliest place in the whole auditory pathway that these sort of binaural neurons or two-ear neurons, right? Where is the earliest place in the auditory pathway they could possibly exist? I want you to pause for a moment to think about it before moving on. So for the answer, you've got to recall something we learned earlier. You've got to recall that early on in the process, some, but not all neurons cross contralaterally. In other words, they go across the brain to the opposite side. We'll see this is very common for almost all of our senses. Now, it doesn't happen in the first stop. It doesn't happen at the cochlear nucleus, right? If you follow the little arrows here, going from the cochlea to our first stop, the cochlear nucleus, you can see that cochlear nucleus is only getting info from its same-sided ear, from its ear, right? It doesn't get info from the other side, nothing. But in the next step up, as soon as we start moving up to the superior olive on each side, right, this is where we're suddenly getting some input to either of those superior olives. We're getting input from both ears. So this one on the left is getting a red arrow and a blue arrow. In other words, it's getting same-sided information and contralateral information. So theoretically, our little neural network that we've talked about for detecting the direction of sound that a sound comes from, that could show up here at the superior olive. And sure enough, these kind of networks have been found. They were actually identified first in barn owl brains as an animal model, but then later confirmed in humans. And where do we find them? Right in the superior olive. So even early on, the brain is already trained to pinpoint where a sound is coming from before passing the rest of that sound information on to other parts of the brain. Okay, but let's get back to those other cues our brain uses for localization, right? Because we saw that binaural cues alone can't tell the difference between, say, sounds coming from above us and those coming from below us. For that, we're going to need other information like monaural or one-ear cues. So specifically, the biggest monaural cue, the biggest help that we have, comes from the part of the ear that we can see, the part that's external. So specifically the shape of the pinna. Remember, the pinna is that fleshy part on the outside that we can see. The shape of the pinna is such that what it does is it amplifies frequencies, and it does so where it amplifies the frequencies differently depending on how far above us or how far below us a sound is coming from. We can actually demonstrate this in a lab study by planting a tiny microphone deep in the auditory canal, like way down by the eardrum, right? So where the sound would end up normally. Plant a little microphone deep inside there and see what kind of sound, what kind of pattern of frequencies and amplitudes, what kind of sound reaches down in there. And then while we've got those microphones in there recording the sound waves, we play an identical sound out in the environment, but do it from either above the person or below the person as a couple different conditions, or, from various elevations. And in this case, what we find, we'll keep the sound straight ahead. So there's no binaural or two-ear cues. But what we find is the same sound coming from above will actually come into the inner ear. We'll get into our little microphone as a very different pattern than if that same sound was played from below. You can see an example of that here for one sound. The same sound being played from a little above versus a little below. By the time it gets deep in the ears, right, it's the exact same at the outside of the ears. Before it bounces around the pinna, it's the same sound out there in the environment. But by the time it gets deep into the ears, where we've planted our microphone, we can see that actually the sound was kind of filtered and attenuated. It was changed along the way, and it's the pinna, the shape of the pinna that actually did this, and it does it in such a consistent way the brain can kind of figure that out. So the exact same bird chirp will actually have a different set of frequencies at different volumes when it comes in from one elevation than if it comes in from another elevation. This is actually predictable enough the brain can filter and correct for that. So we'll still recognize it as a bird sound, and we perceive it the same. It sounds the same by the time it's processed in the brain at the level of hearing it. And yet we can see here from the frequency information, there's actually info in that early waveform of the sound that tells the brain if it's a from above kind of pattern or a from below kind of pattern. Now, other experiments have confirmed this with a pretty creative method. First, before doing anything else, before really starting the experiment, what they do is get some baseline measurements. So they measure how well a person can localize elevation by playing sounds at various heights. And they'll play it, left or right or things like that too. But the key part here is they'll play it from, 30 degrees above or 30 degrees below or straight on at various heights and see how well the person can figure out the height it was coming from. Then what they do to start the actual experiment is they put a mold in. They put a little mold into the person's ear that changes the pinna shape. And the person's going to wear that for a few weeks. Now, initially on that first day, right before they've had time to get used to it, so right off the bat, initially, right after putting the mold in, people are actually... They're fine at left-right location info. They're fine at figuring out whether sound is coming from the left or the right. And that's because they can still use binaural cues, right? Those still exist. Nothing changes with the mold there. But now they suck at localizing elevation. Their performance is horrible. They can't tell if a sound came from above or below. Now the sound is still getting in, but now it's not being bounced around by the pinna in a way that the brain has been used to for all those years. But over the days of the experiment, over the weeks, the person gets better and better as their brain adapts to the new pattern by which the new molded pinna bounces and attenuates sounds. In fact, by the 19th day, participants were almost as good at localizing whether sounds coming from above or below as when they started and were using their natural ears. So our brain just has to adapt. It has to pick up as a sort of pattern recognizing device. It picks up on the pattern of, okay, now that I've got a pinna of this shape, it attenuates sound in this way. It does it so consistently the brain can pick up on that pattern and basically say, oh, this is the same sound, like a bird chirp, but coming from above, right? So it changed the sound a little bit in this way, because that's what happens if anything's above me. Or this is that same sound, a bird chirp, coming from below, because there was a kind of predictable change, a pattern of change of frequencies based on how it bounced around. The brain can get used to a new pattern, a new pinna shape, which is nice. And actually, interestingly, when they took out the mold and went back to normal, people with their normal natural pinna shape, they got worse at the task briefly. For a bit, people were worse at the task, but very quickly returned to normal performance. It seems that they didn't take weeks to go back to that. So it seems that the original sort of decoding algorithm, the original understanding the brain had for making sense of up versus down frequency changes, that was still stored somewhere in the brain, able to be sort of activated. Like, oh, we're back in this mode now, turn this mode back on. So very quickly the brain goes back to, oh yeah, this is familiar. I can make sense of up and down sounds with my usual pinna shape. Now, you can actually find some fun demos on the internet showing how sound engineers can take advantage of things like binaural cues to simulate sounds through headphones as if they're coming from the left or the right in a way that feels very compelling and very three-dimensional. So rather than just playing a sound on the left headphone to make you hear it as coming from the left. What they actually do is they play every sound on both sides, coming out of both the left and the right earphone or earbud, but with a little bit of interaural time difference or interaural level difference. In other words, play the same sound but with a slight time delay and slightly quieter on one side. And these simulations, they work best with headphones. They're set up for headphones. So for those of you listening who might be using headphones right now, I'm going to play about a 1-minute snippet of one of these that simulates being in a barber shop and someone kind of walking off to your right and then coming back and doing something to your left and your right. But if you don't have headphones on right now, don't worry about it. Just you can come back to these or find examples of these online later when you have headphones. So let's play an example of this just to kind of see what I'm talking about. Maybe I'll just skip a little ways in here and play one of these.
The only reason I did that is because all of the fancy barbershops do that. What you're listening to as I move off to your right here is very quickly washing my hands. Manuel, could you get that, please? Oh, thank you, Manuel. Let me finish washing my hands. Just bear with me for a few more seconds. Ah, there we go. Ah, yes. As I was saying, all we are doing is using your head as the listening point. And we have two microphones, one on either side of the head, in the same position as where your left and your right ears are.
Anyway, you get the idea if you happen to have headphones on right now. I've got the full thing for this one and a link there in the slides, but you can find those just by Googling online. For now, though, there's something else I want to point out about how the brain does auditory localization. Remember that the main initial processing area for sound in the brain, in the main part of the brain, is A1, right? What we call the primary auditory cortex. I mentioned that from there, info then gets processed nearby in areas like the secondary auditory cortex. That was the blue part in this picture we saw earlier. Well, from there, it also gets shared with other parts of the brain. Otherwise, we couldn't really use any of that auditory information that we heard, right? It has to go to the language areas if we want to understand the sounds as words and choose our reply. It has to go to the motor area if we want to react to the sound by walking towards the source or away from it. It has to combine with info from the other sensory areas if we want to form associations between like what an animal looks like and what it sounds like or what sounds it makes. So, well, it turns out the wiring coming out of the auditory cortex, like the wires that go to other parts of the brain, it actually has two major streams, two major directions or bundles of wires that the info goes from here to when it comes from the primary auditory cortex. Some signals get sent kind of forward and down towards the rest of the temporal lobe. There you kind of see in green here. So the A in this diagram is for anterior, which means forward. So this signal is going down and forward. But other signals, another bundle of wires, another main pathway for that info, is signals getting sent back and up toward the parietal lobe, which is up there at the top of our brain. The P you see here in the diagram is for posterior, which means backwards. So this is a signal going back and up. Now, both of these two streams also do send information to the frontal lobe so that we can use that info for planning and integrate the info across time and stuff. But we really got these main two primary streams of information, these two primary ways that information flows coming out of that initial auditory processing area, that initial auditory expertise area in the brain. So some of it's going deeper down into the temporal versus up into the parietal, and those actually seem to be a fundamental part of the wiring that we have for all of our senses. All of our senses we're going to see kind of send their information, some of it sort of down into the temporal lobe and some of it up to the parietal lobe. So I just wanted to preview it here, and then we'll see it again when we cover other senses. We've identified these two streams or these two pathways as having different functions, different ways of using the auditory information. And initially, we actually learned that through experiments with animals, specifically a lot of experiments in cats and ferrets as a mammal model, where scientists have temporarily turned off one pathway or another by basically cooling that brain area down. It's like a temporary, less invasive version of what's called lesioning, causing a lesion. Usually a lesion would involve actually damaging that brain area in an experiment, like scooping it out, injuring it in some way, getting rid of it. But nowadays what we often do is we simulate that. We can actually just cause temporary brain damage. It doesn't have any lasting effects, but basically just temporarily turn off an area of the brain, creating a sort of temporary lesion, but such that after the experiment is done, that area is back to functioning normal and everything's back to normal and no damage is done. So it turns out when you temporarily lesion the back areas, that sort of back pathway in the posterior direction toward the parietal lobe, our test subjects, these animals, suddenly can no longer localize sounds, though they can still identify what a sound is. So they can tell the difference between a predator sound versus the sound that they know means I'll get a treat in a second or whatever. They can no longer do spatial things with the sound. They can identify it, but they can't tell where it's coming from. But when you instead lesion or turn off or damage those more forward areas, right, in the anterior direction toward the temporal lobe, going down and forward, that other pathway, then these mammals suddenly can't identify what a sound is. They can't tell the difference between a scary sound, a happy sound, a sound of a predator, a sound of a treat, anything like that. They can't identify sounds, though they are able to localize it in space just fine. They can tell if it's from the left or the right. They just can't identify what something is. So, from our primary sensory area, from all our primary sensory areas, but in this case, from our sound area, the pathway going up and back to the parietal seems to be a sort of where stream of processing. It processes where that sensory info is coming from. Or in other words, it has a sort of spatial interpretation. It uses it in spatial ways. Whereas the other pathway, the other bundle of neurons, the pathway that goes kind of down and forward to the temporal lobe, seems to be what we might call a what stream of processing. In other words, it takes the info from a sense, in this case our auditory sense, and uses it to recognize or identify or conceptualize things, to say, oh, this is what something is. And yes, those studies were done on animal models with other mammals, not humans. So you might be skeptical and be like, well, does that apply to us? You can actually see a cat brain here, for example, which looks a little different from ours, although the layout and function is often very similar for basic stuff. There's what we call homologs, or kind of same areas across those brains, but we've actually confirmed this dual pathway layout in our own brains too, with evidence from humans who had brain damage to one of those two areas, like in an accident or a stroke. That's what neuropsychologists study. We've also done this through like neural recordings of people during brain surgery. So if they're awake during brain surgery, you can kind of poke and prod and try out these different areas and see what they experience. Or we've also got evidence coming from brain scanning on healthy brains, no damage or anything, so there's normal healthy people, while they do like a sound location task or a sound identification task, and see which of these bundles or which of these pathways lights up or has activity during those tasks. And as I said, we'll see the same dual pathway layout for our other senses when we get to those. Meanwhile, though, there's one last thing I want to talk about with auditory localization before we move on, and that's how we deal with echoes. So think of it this way. When we're outdoors and we make a sound, or if we hear something else that's making a sound, the sound is generally just kind of going off in every direction, but we're just hearing one direct copy of it. In whatever direction we're sitting, right, we would hear the sound. Like you can see with this red arrow here, someone playing guitar, we hear the sound that came straight from the guitar to our ears. But when we're indoors or in other enclosed spaces, or if there's walls or buildings around, sounds not only travel to us directly, like in the first line here, the one highlighted in red, but we also get a lot of reflected sound that gets to us indirectly by bouncing off of walls and ceilings and such. So why do we only hear one sound? Of course, when we have a conversation or listen to music indoors, we don't usually hear 50 echoing copies of every single word or note. Right? We don't perceive each copy of the sound, nor do we get confused when most of the sounds come from directions other than the source, like when they bounced off of a wall to our left or a wall to our right first. So you might take a moment here and speculate on why we only hear one sound and what info our brain might use to help us distinguish the direct sound from all that indirect sound, all those echoes or copies. So pause the video now and give it some thought before moving on. Okay, so you may have correctly surmised that the direct sound, like the red line here, it's going to reach our ears earlier, right? It's going to reach our ears first and the others will come later after a delay or a little bit of lag. So that means it'll also be louder since it hasn't traveled as far, been absorbed from the objects it reflected off of. But actually that time difference alone, the fact that it gets to us first, that direct copy hits us first, that alone is enough for our brain to figure out, to distinguish direct sound from indirect sound and to help us not interpret or hear, perceive all the echoes. So this was confirmed in the laboratory by Litovsky back in the 90s by setting up an experiment where sound was played from both a left speaker and a right speaker that were equidistant to the person. But they played it with a little bit of a delay on one side, basically simulating the direct sound and then an indirect copy of the sound as if it had bounced off a wall on the other side first. The key is when Litovsky used a long delay, a long lag between when those speakers played that same sound, like a tenth of a second, right? 100 milliseconds, 100 thousandths of a second would be one tenth of a second or longer. What happens is we actually do hear it as an echo. We hear both copies. But when using a very short delay, like 5 to 20 milliseconds, we perceive a single sound. And what happens is the brain just ignores the lagged copy, or copies. We've done this with more copies now. But the brain ignores the ones that come in a little later. It ignores the indirect version as long as they're happening pretty quick, which is what will happen in any kind of small room that you're in, or normal size room that you're in. This is called the precedence effect. We only perceive the sound that's coming from the source that reaches our ears first. If other copies of that, echoes of that sound come in very quickly afterward, the brain literally just ignores them. They don't go further into processing and reach the level of us perceiving it. We don't have an experience. We don't hear those copies. Even though the sounds got into our ears, it doesn't get processed at the conscious level. And this knowledge is actually used a lot by architects now when they're designing things like auditoriums. A lot of auditoriums and performance spaces may actually be designed to avoid the precedence effect and make people perceive the echoes or reverberations if that's desirable. It's bad. So having those echoes, having those reverbs, right? Having it that way, like it's bad for perceiving speech. You won't be able to understand what people are saying in a big room like that. Like if you're in Notre Dame Cathedral or something like that, it's really hard to hear what people are saying if they just give a speech, but it's ideal for certain musical effects, like an impressive pipe organ, right? That has like a full, rich sound. Okay, anyway, let's move on for now. Enough about localizing sound. We're gonna finish up Audition in the next video by seeing how our brain accomplishes a very hard task, a very real world task, making sense of complex real world auditory scenes where like a bunch of things might be making sounds all at once. And as I said, we'll tackle that in the next video.